Welcome to the pressure unit. First up, we learned about fluids. All fluids can flow. That means they can move, fill, and take the shape of their container. Like a gas can fill a balloon or water can fill a bottle. And they all exert pressure, like water exerting pressure on this fish. Now, how do we calculate pressure? Here's our equation. Pressure equals force, which is in newtons, over an area. In our case, probably meters squared. Let's take a look. Here's an aquarium. We have two fish inside. Now the water is exerting pressure on the fish, but it's also exerting pressure on the aquarium. Let's take a look at calculating the pressure of the water on the aquarium. Say we have 50 newtons pressing on the bottom, which is 4 meters squared. Let's do the math. 50 divided by 4 is 12.5, and we measure that in pascals, PA for short. Now that we know what pressure is, let's take a look at pressure around us. First off, look at this picture. There are particles of air up near the clouds, near the mountains, all the way down to the ground where there's water. Now those air particles actually create pressure and cause pressure, and it's caused by gravity. Very much like this cake. Take a look. If you look, the top layer exerts pressure on the bottom, and both layers exert pressure on the most bottom layer. This pressure is all because of gravity. Let's go back to our picture. If you notice, all the air particles on the very top are spaced out. As we go down, they become more compressed and there's more pressure. We can measure that pressure. At the outside of our atmosphere, there's 0 kilopascals. We said this is 0 atmospheres of pressure. As we move down towards sea level, pressure increases to 101 kPa, or 1 atmosphere of pressure. Again, remember the cake. All the air particles are being pressed down. If we go below sea level, 10 meters, we are at 202 kilopascals, or 2 atmospheres. We go another 10 meters to 20 meters, we're at 303 kilopascals, or 3 atmospheres of pressure. Now, if we were to dive to the bottom of the ocean, right, all that pressure would be too much for our body, and crunch, we would implode. If we were to go into space, or like this ball, have too much pressure, we would end up exploding. One thing we learned is about buoyancy, or the fact that fluids, such as water, can press back on an object. We call this buoyancy if it's on the bottom of an object. Take a look at this boat. The water is pressing on the bottom of the boat, and that helps keep it afloat. Now think about it. If the gravity, the force downwards, is greater than the buoyant force, an object sinks. If, let's take a look at this duck, the buoyant force is greater than the force of gravity, it stays afloat. Which brings us to our next principle, which is Archimedes' principle. If we take a look, famous for Mr. Archimedes is Eureka in a bathtub. If we place an object in water, right, that water level rises. Now, if we were to measure the amount of water that rises, we would find that it is equal to the amount of the buoyant force, and that's known as Archimedes' principle. Take a look at this example. If we have a guy who weighs 100 pounds, we'll call him Tim. When he's in water, he weighs 80 pounds. So a change in 20 pounds. Now that change in 20 pounds is equal to the water that spills out of the cup or out of the tub because of Tim. Again, this is what we call Archimedes' principle. The next idea we talked about is fluid motion, whereas areas of high pressure always move to areas of low pressure. Take a look at this tire. It has 32 psi. I know it's not pascals, but something we are familiar with. If an arrow is shot at it, think about it. There's a lot more pressure in the tire than the atmosphere around it. So the pressure in the tire, which is higher, leaves and moves to the area of low pressure. We used a couple of different examples, such as the vacuum. Take a look. When it's off, all the pressure is the same inside the vacuum and outside the vacuum. We represent these particles as being equally spaced out. When we turn the fan on, the fan pulls the particles, creating an area of low pressure. Now the surrounding area outside the vacuum hose has higher pressure because it's not being pulled by the fan directly. So since the area outside the vacuum is higher, it wants to move into the hose and fill that low pressure area. And while the vacuum stays on, this low pressure system is going to stay there. The second principle we talked about is Bernoulli's principle. And this we talked about kind of the lazy river, and we've talked about a couple different things. But it states, as fluids move, pressure decreases, or areas of low pressure are created. Take a look at our lazy river again. As it's wider, there's our guy in our tube. Okay. The water's moving slower and there is higher pressure. As soon as it narrows, the water is actually moving faster and actually creates a low pressure. Think about the particles around that faster moving water. They actually come into the current and they're taken away because it has low pressure. Again, high pressure wants to enter areas of low pressure. This is part of the reason why when we get to an airplane wing, if you take a look at the arrows on top of the wing, they have to go a longer way and their area is cut down to a smaller portion. So those top arrows need to actually squeeze through and actually move quicker. And again, thanks to Bernoulli, quicker moving fluids create low pressure. On the bottom, there isn't much change for those two arrows of particles. So the pressure is higher. Again, higher pressure wants to move to low pressure, so the wing here, the cutout of a wing, actually makes the plane move upward. Now there's more to it than that, but this is a simple example of Bernoulli's principle. The last thing we're going to learn is Pascal's law. Now it talks about having a container that is fluid filled and it's closed, meaning there's no open holes, there's no exit. Now if we apply a pressure to one side of that closed fluid filled area, pressure is exerted equally on all sides. If you take a look at the jar, there's an up arrow, down arrow, left, right. There's pressure all around in equal amounts. Now this is super important when we get to tractors trying to move the arms, moving the bucket. There are fluid-filled lines that are actually controlled by joysticks inside the tractor. Shocks on a bicycle, a car. If you take a look, those two pistons are attached to fluid-filled containers where they can't escape. So if a tire hits a bump, it presses up on those fluid-filled shocks, and the shocks, the pressure exerted equally and actually presses down. So when you hit a bump, the shock goes up and then back down because they're fluid-filled. Now, one example we're going to talk about is cars. How does that work? Take a look at this driver. He presses on the brake pedal. It presses a fluid through the brake lines. And on the opposite side, the pressure can't escape, but it does move and actually presses the brake against the tire. So what happens is we apply a force to one side of the container. The fluid moves, or in this case the particles, whether it's hydraulic fluid, brake fluid, water, air, and it causes a force on the other side. Now we can use that to many advantages, and we do for lifting cars, on hydraulic lifts, again moving the tractors, shocks, and we'll talk about some more in class.